Hello and welcome to today's webcast, Put a Dent in Your CSO Event Using Structural HDPE, brought to you by Waterworld and sponsored by Uponor Infra. My name is Angela Godwin. I'm Chief Editor for Waterworld, and I will be your moderator today. A few housekeeping items before we begin. At the bottom of your audience console are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We'll try to answer these during the live Q&A portion at the end of the webcast, but if we don't get to them, we will provide those to the speakers and they will answer you individually. You can expand the slide area in the center of your console by clicking on the maximize icon at the top right of the slide window, or by dragging the bottom right corner to enlarge it. In fact, you can expand and reposition many of the components you see on your screen, so please feel free to arrange them as you desire to give you the optimal webcast viewing experience. You'll find some useful resource materials available for download via the resource list widget, which looks like a green folder at the bottom of your screen. There you will also find a PDF of today's slide presentation. If you have any technical difficulties during the webcast, please click on the Help widget. It has a question mark icon and addresses some common technical issues. But if you still need assistance, just type your issue into the Q&A widget and a member of our webcast support team will work with you to correct the problem. For your convenience, this presentation will be available on demand within 24 hours of the live event. A reminder email message will be sent out to all registrants with a link to that archive. It will also be accessible from our homepage at waterworld.com. One last thing to mention, the presenters will be issuing a certificate of attendance to all attendees within 48 hours of the conclusion of the webcast. We have two terrific presenters for you today. We have Grant Thornley, who is the Director of North American Sales for Uponor Infra. With 25 years of experience in the industrial, municipal, and power markets, Grant's area of expertise is in pipeline infrastructure rehabilitation, asset management, stormwater, wastewater management, water transmission, and condition assessment. And we also have Brian McGuire, PE. He's a manager of engineered systems in North America. He oversees product development, sales, marketing, engineering, and operations related to Uponor Infra's engineered system portfolio throughout the region. He's a licensed professional civil water resource engineer with over 20 years of experience in the civil construction materials industry. And now, without further ado, I will turn the program over to Grant.
Great. Well, thank you very much, Angela. I appreciate that introduction. And I'm I'm trying to push the slide here. There we are. Okay, I thought we would start very quickly with the agenda. We'll do a quick introduction of who Uponor is. We'll get into a bit of the Waylight introduction, an overview of our engineered systems, move into our CSO and stormwater applications, and then slowly move down into the benefits features, the engineering, and finally application examples of applications. To start off, who is Uponor Infra? Well, we started back in 1918 as a carpentry workshop and really fabricating furniture, beds, and furniture. One of the aspects of our fabrication was we actually made the steel bed springs. That fabrication of the steel bed springs evolved in 1938 to the manufacturing of cast iron pipes, which is our first foray into the infrastructure market within Europe. Later on, steel pricing increasing within Europe, we expanded our portfolio to start producing PVC piping because of the economics of it. Continued the expansion of our technologies as well as our market. We went into PEX piping. Continued the demand for infrastructure rehabilitation continued. In 1999, Uponor started to begin acquiring several other companies, and one of the largest companies that we purchased within the pipe manufacturer was KWH, which a lot of people knew us back then by. KWH has specialized technologies as well as patents within the manufacturing of large diameter HDPE pipe using a technology called Waylight. And today, Uponor offers numerous polymer solutions, and we have expanded beyond just pipe offerings for the infrastructure, and now do more solution offerings for stormwater, wastewater, but structural elements offerings. So Uponor, just as a general, we're about a I'll convert that to euros to US, to about 1.1 billion US. We operate within 30 countries. We have 14 manufacturing facilities worldwide, as well as a couple in North America, and have over about 3,700 employees. Uponor is broken up into three divisions. Uponor Infra Solutions, which we represent, is about 30% of our operations. 45% is about in plumbing solutions, and 25% is indoor climate solutions, which are electronic controls for heating, cooling, and so on. To understand, Uponor Infra, our offerings within the North American market space, we can really break it into three families of three different types of products. One is, you're probably familiar with our Sclair pipe, which is our solid wall HDPE, high-density polyethylene, which allows us to go from small diameters, about 3 inches, to about 63 inches on the solid walls. And that allows us to go from lower pressures to very high pressures, over 200 psi. The structural HDPE pipe, which was a unique offering by KWH, that allows us to do high volumes but lower pressures. So it allows us to really look at the market space of what is the most economical offering to put forward, and that's we classify as our Waylight pipe. Examples of the Waylight pipe would be in gravity, stormwater drains, as well as using them in hydroelectric for penstocks, the conveyance of water or wastewaters. And lastly, our structural HDPE panels really leverages the technology of the Waylight the technologies that we have, and allows us to produce panels. The combination permutations of doing a solid wall to a structural Waylight pipe to the panels really allows us to go to the market and provide very unique solutions offerings out of the structural HDPE that no other company today offers within North America as well as Europe. So to start off with, the key component that we start off with is a box beam structure, which is extruded out of our extruders. That's the base component of our Waylight pipe, as well as our Waylight pipe, as well as our Waylight panels. Just a quick diagram of this. You can see one of the Waylight pipes. If we were to weld the box beam structures together, we can create larger structures, and roll that. If we take the box beam structure and put that onto a winder on a helical drum, we can wind that into a very large diameter pipe, or we can weld it just in a straight plane and produce the Wayo panel. So there's just two pictorials of the raw materials that we're looking at. Here's one of the Waylight pipes coming off of one of our production lines. This is a smaller one, but we can produce up to 14-foot diameters. Getting into the properties of HDPE, there's different types, like anything from back in the 1920s to present day. Technology's evolved, and so has the chemistries within resins. Uponor uses a bimodal resin, and simply put, what that is, it provides us a resin that has greater structural properties than a unimodal that is commonly found in the market today. It provides greater structural integrity, greater resistance to crack propagation, better stress ratings, and so on. The other aspect to Uponor, we don't use any regrinds or any filler in our materials, which allows us to have very tight control over the characteristics of our products. Just to give you an understanding of HDPE, some of the characteristics, which is the creep and stress relaxation. Typically, this pictorial here shows you that if we were to apply a strain or force to the material, it will react by elongating and trying to counteract those stresses. So in this particular instance, over a long period of time, the material will compensate by stretching out to try to alleviate the stresses applied to it. That being said, that the material essentially has a memory, so when you release the stresses that have been applied, it typically goes back to its original form even after 50 years. So that is important, an important aspect of the HDPE material, because other rigid materials, you would develop stress points and could create stress fractures or cracks and essentially leak points. Oops, sorry about that. One of the other aspects to HDPE is its chemical inertness. Because it is an organic material, and the HDPE principles, it's unaffected by acid and bases. So if you had pH swings from very low to very high, it's inert to those, which is great for wastewater treatment or chemical batch tanks, or even stormwater systems. Unaffected by hydrogen sulfide, particularly in the vapor space or on the crown of pipes. It's unaffected by that, unlike steel or concrete. And again, because it's not a metallic material, it doesn't suffer the effects of corrosion. One of the important aspects when we talk about stormwater applications, or CSOs, is the abrasion resistance of HDPE. When we compare, whenever you have particles impacting, such as sand or silt, the rubbing or the impact of the solid upon the pipe structure's surface will result in abrasion. So here's a quick pictorial or graph of showing that when sand or hard material impact concrete, the wear or abrasion of that surface is quite rapid, whereas HDPE, because it is more of a flexible material, actually absorbs the energy of those particles, and less abrasion occurs within those surfaces. And that's important with stormwater or CSO applications, because you are passing through sand and silt through the surfaces. So those are just quickly some of the characteristics of the HDPE. Really, what our foray or value offering to the market space is the fabrication and welding of the solid wall, the waylight, and the panels into very unique configurations. And from those configurations, what Uponor has evolved over the past couple of years is our engineered solutions. Our engineered solutions, here's a couple of pictures of a couple of tanks, either barrel, square tanks, a geothermal vault. The versatility and the design aspects, we have a 100-year design life of HDPE. We work because of the fabrication, the abilities. We were into numerous markets such as stormwater, CSO, rainwater harvesting, pump stations, wastewater, anything that requires the conveyance, storage, or retention, detention of a liquid. We can design our systems and custom make it to whatever the engineer's requirements are. Here's a collage of a couple of examples of the fabrication abilities that we have. This is a simple barrel design. Here we have a manifold. This is typically a stormwater detention. Increase in the barrels increases the capacity. An example of fabricating angles or fittings. Here's a square. Another one is a manifold design. To give you an example of, again, our fabrication facilities, again, there's really nothing that we can't do, and what we say around our engineering is that we're limited by our imagination. Another collage showing a couple of examples of the bending radius ability of the waylight pipe. Additional, here's one of having a reducer, of taking a pipe and reducing it down using the waylight. Here is a manhole or surface entry. Another one here is a manifold configuration, and you see a service ladder coming in here. So working with the engineers, again, there's the versatility and the flexibility within our designs, just to give you an example of what our capabilities are. For one example, here is a retention. just a straight barrel design to show a straight capped on both ends with a service way. This is intended to be buried. Another, if it made more, sometimes if the space constraints are high, we have a smaller footprint in which to work with a large volume. Square tanks are an ideal solution to that. Here we have I believe it's a 14-foot high by 14-foot detention tank, about 56,000 gallons. And for this particular, we can see that we put flange fittings onto the front. Another exploded isometric view. This is again to show our capabilities. This is the stormwater, and you see this particular design, we've actually put baffles into it, which allows the impact of particles, allows more of a rapid settling rate of particles, so we have cleaner effluent coming through. And you see down here we have a tapered area, so sedimentation and particulate can be flushed out by these flush ports at the very end, very bottom. Another configuration design. This is a manifold, again showing the flexibility in our design and an options we can provide. In this particular one, the yellow, you can see that we've installed this that provides channelization of low flows, as well as here's an access point for the FRP ladders. This is a pump station. It's on a horizontal. This would be installed vertically, but here's an example of about a 10-foot diameter pump station. And this particular, rather than a manhole, we've put actually a metal surface entrance on there. And I think Brian will be getting into this flat bottom right here. This is a anti-buoyancy device. This is to show, again, different flexibility and configurations that we have. These are being welded on site, but here you can see here's a manway entrance that's a little bit different. Rather than having a concrete configuration or pour, this is a little bit more unique and allows, again, smaller, depending on the footprint. This allows us a more tighter footprint and more accessibility, more variabilities in the accessibility of our systems. This particular example, this is a UV system, but it's to show the combination of combining the whale pipe as well into our whale panel to produce a UV system. But again, it's to show you the combinations of the two materials and the integration that we can provide. And from there, I'll turn it over to Brian.
Well, thanks, Grant. I appreciate that. So what we're going to do now is, after we've had a brief overview of the material, its capabilities, we're going to cover how the material, both in round and rectangular form, can be used to provide solutions for both combined sewer overflow and stormwater detention and retention structures. We're going to spend a little bit of time discussing some applications and configurations, and then we'll cover some of the design and technical aspects of the system. But basically, wheelite and wheelite modular rectangular units can be utilized to provide solutions for combined sewer overflow, wet weather facilities, peak flow attenuation, vertical pump stations, and manhole applications. And as Grant mentioned, our resistance of the material to hydrogen sulfide, pH, deterioration, and corrosion makes it an ideal solution for wastewater applications and combined sewer overflow projects. We also can produce large-scale stormwater management facilities with both round and rectangular systems. Detention, where we're not allowed to leak or infiltrate water, similar to combined sewer overflow, or retention, where we're actually trying to accomplish infiltration. We can also manufacture outlet control structures, junctions, and internal baffle walls to promote TSS debris, trash debris, and other contaminant removal. So again, as I mentioned, we have two solutions, and Grant kind of covered this. We have the wheelite large diameter round storage structures where we could produce manifolds in up to 132 inches or 11-foot diameter. We're one of the few manufacturers in the world that can produce detention and retention structures of this scale. And depending upon diameter, soil condition, and water table, we can accomplish depths of up to 50 feet. So that should give us an understanding of the robust nature of this material and its ability to be used in a wide array of applications. Large diameter, deep structures, incredibly strong. And again, we can accomplish inlet-outlet configurations, control structures. For detention projects or CSO projects, we would utilize a field-welded joint, and we'll cover that in a little bit more detail. For retention structures, we have a threaded joint, and we'll review that as well briefly. On the round side, we have what most people would consider as a round storage option, which would be a single tank. And these next few slides kind of demonstrate some configurations that we could accommodate. But because of the versatility of the material, we can essentially produce almost any layout configuration necessary to support large volumes of storage given the existing site conditions. And this is the beginning of what one would see as a simple singular tank. One single 11-foot diameter tank, about 50 foot long, would be the limit on what we could ship to the project in a single load, and that can provide about 35,000 gallons of storage. However, if we require additional storage, we can connect those systems in the field, either end-to-end using extrusion welding in the field, which we'll cover, or with large diameter or small diameter manifold header systems at the ends to connect them hydraulically. Again, this just kind of reinforces that infinite configuration of large diameter round storage structures. Here you can see on the left-hand side of the slide we have what is referred to as a large diameter header or manifold. There's also the option to do bulkheads, and you'll see in some photos to do a bulkhead end and then connect those sections using a smaller diameter pipe, and that tends to be the more cost-effective approach from a material and fabrication standpoint, to use smaller diameter headers as opposed to larger. But occasionally site conditions, layout configurations require that we squeeze a little bit more storage in the end of the structure, and we can do that with a large diameter header as you see there. Here's just another example of the infinite configurations we can provide. This is just a simple 3-barrel manifold system, and then obviously that can grow to accomplish whatever you require for your given site. If you have a rock bearing or water table issues, you want to keep the system up high, we can lay the structure out to accommodate whatever volume of storage required. We can also do manhole risers to provide access throughout the structure. We'll cover manholes in a little bit. So that should give you a brief snapshot of the wheelite detention structures from a round perspective. But what most people aren't familiar with is our ability to produce modular rectangular storage units. Our development of this product began and actually was available to the market space in about 2013, and we've been developing this technology over the years to bring it to the market space and have it available for stormwater and CSO applications. What we can do is we can manufacture extremely large rectangular units. The largest we can ship is about 49 feet long by 12 feet high and 12 feet wide, providing about 53,000 gallons of storage per single unit. If we need more storage, just like the round, we can connect those units hydraulically with pipes and extrusion weld them in the field to ensure we have a complete watertight system. This is unique and previously unavailable. Prior to the development of wheelite modular, the industry was left with structures like this had to be concrete just because of the volume of storage and size. However, those concrete structures would be cast in place in the field due to the weight and difficulty handling and shipping structures of that magnitude. Because we are 1/10 the weight of concrete, we can now produce extremely large rectangular structures, much lighter than concrete, with a 100-year design life, immune to hydrogen sulfide, deterioration, corrosion, and they are a system that is extremely versatile and can be designed to meet your site conditions and provide the volume of storage that's required. Here's a couple examples of how that rectangular configuration could be expanded, providing in this particular example 9 units to achieve a volume of storage for a particular CSO application. And this obviously is just one example, and we can expand upon that. Here you see a photo of a dual structure systems being shipped out to the field. Those 2 units would be end-to-end connected, and we provide an inside and outside fusion weld to connect the two structures to provide one continuous rectangular storage structure in the field using the wheelite modular application. But that's not the limit of it for storage. Anything that you can think of that you would have approached with concrete, steel, fiberglass, rectangular structure, we can now manufacture out of wheelite modular. When design loads require, whether it's airport loading, CL625, HS20, we can reinforce the annular space to accommodate those loadings and ensure that the structure is within allowable structural tolerances or max deflection. So again, if you can think of a project that would be a large rectangular structure, the chances are we can manufacture it out of wheelite modular. Both round and rectangular options, whether you're wheelite round or wheelite modular, can be fabricated with internal controls, baffle walls to encourage TSS removal or particulate separation. We can also provide energy dissipation inside the structure, and we can do outlet control. So if you're in stormwater situation, you want to provide peak flow attenuation, low flow, mid flow weir controls in a wall, you no longer have to build an independent rectangular concrete structure. You can do all that inside your detention structure and do so much more cost effectively with wheelite's capabilities. So we mentioned a few joint configurations. We have basically threaded, which is a soil-tight joint, and then we have welded, which can achieve pressures up to 22.5 psi. And we'll talk a little bit about each one of those independently. Our threaded soil-tight joint was originally developed for culvert reline applications where they're going to grout the annular space around the structure. We do quite a bit of culvert reline projects. However, it also is functional for retention applications where we're allowed to infiltrate, and we're going to design a system that has a clean graded aggregate backfill around it, surrounded by a geotextile fabric. We want to store water in the detention structure, but we also want it to infiltrate, and the soil-tight joint can be utilized, and the threaded joint can be utilized in that configuration. However, if you're in a wastewater application or a detention application where you don't necessarily want to infiltrate, you're going to go with a field-welded joint. And we have a number of different joint configurations depending on your application and the pressure requirements, essentially. We can start with a single wall, ID or OD, which is where we'll either weld where the pipes come together. We'll either weld the inside of the pipe or the outside only. And that gets us to about 5 psi with standard wheelite. We can do an inside diameter and outside diameter weld, do both welds, and that's going to get us to about 10 psi with standard wheelite. If we want to achieve higher pressures, we have a product called Wheelite LP, which essentially is a slight modification to the extrusion process where we would smooth the weld, the profile-to-profile weld or annular section-to-section weld to achieve a 15 psi. With that pipe, we would also have what's referred to as full penetration weld, where we have a mechanical welder that goes out to the project site and welds the two materials together to ensure we have a full penetration weld. We also have Wheelite LP 1.5 that in combination with our mobile welder can achieve a 22.5 psi. There are obvious costs associated with each one of these ratcheting up in pressure capabilities, and we would take a look at that with you when we work through a project to determine what the requirements are and what was necessary, and then develop a specification that met your requirements. Here's a snapshot of an extrusion welder, and we'll talk a little bit about extrusion welding, but an extrusion welding technician doing an inside diameter extrusion weld. On the right-hand side, what you see on the left-hand side is our coupler. That's a temporary band that holds the pipes together in the field while we do the extrusion welding. So basically we do a butt-end connection, lock the two pipes together, and then do an extrusion weld in the field, and then that coupler can be removed because it is not necessary after the weld is in place. One thing on both stormwater and combined sewer overflow projects and just regular projects in general that are conveyance, we do quite a bit of. We do manholes. The nice thing about our capabilities in manholes is that we're able to produce extremely large, complex geometries. You can see on the bottom right-hand side there we have a fairly complex junction structure that to produce that in concrete would be extremely difficult. However, because of the versatility of polyethylene and the wheel-like material, we're able to produce very complex, large-diameter junction structures efficiently. And again, as Grant mentioned, immune hydrogen sulfide, deterioration, pH, and corrosion. This next slide just shows some of the junction capabilities, and again, we can produce junctions of this geometry and others in large diameter up to 11-foot diameter. We also do pump station wet wells, duplex submersible pump stations. Actually, this, what you see here on this isometric, is an example of a quad pump station, or quadplex, if that is even a word, submersible pump station. On the right-hand side, where we'll actually fabricate all the internal piping components. Base elbows are prefabricated into the system. And all that has to happen once the system is delivered to the project location is the pumps, submersible pumps, are slid down on their guide rails and locked into place. The exterior piping is connected. It's wired to the control panel and backfilled, and they're ready to go. So it significantly reduces the time and cost of installation. And pump station wet wells, we can manufacture up to about 50 foot in depth and 11-foot diameter, complete polyethylene pump station that, again, is immune hydrogen sulfide, pH, corrosion, deterioration. And we find that this is resonating quite loudly with our public service districts and municipalities who are faced with replacing concrete pump stations and manholes that have deteriorated well in advance of their expected design life. So we can produce pump station wet wells as well. One thing to note with our pump stations, it's an important thing that comes up, and we get the question from time to time, as you would expect, if I have extremely large pumps, high horsepower pumps that are anchored into polyethylene, that are rocking on and off and have vibratory loads, we want to counteract those vibratory loads and that thrust of the pump with a concrete base. So what we do is we actually will encapsulate a rebar reinforced concrete base into the system. We'll drop our anchor bolts in to support the breakaway fittings, and we'll ship the system out to the job site with a cast-in-place, fully HDPE encapsulated base that will resist the vibratory loads of the pump and ensure the system will last 100 years that we want it to. And the next slide is just an example of that fabrication with a finished product on the right-hand side with a simplex submersible breakaway fitting that's anchored. As you can see there, the concrete's being cast, the anchor bolts are set into the concrete, and the system is actually fully encapsulated in HDPE. So we still get a 100% HDPE vessel, but we do have that concrete vibratory load resistance cast into the bottom of the structure. And that concrete, in case anybody's wondering, is typically sized to 4 times the pump weight as a standard in accordance with AWWA. So now that I briefly covered some stormwater and CSO configurations from a detention, rectangular, and round application, I'd like to briefly cover some technical considerations related to these systems, as this is a technical webinar. We want to cover some of the critical components related to the design and manufacture of these systems. And probably the biggest one to cover is just some fundamentals regarding thermoplastic welding and fabrication. It's important for us to get an understanding of the nature of thermoplastic welding and fabrication, and also some of the quality control standards that are in place. So for those that aren't familiar, thermoplastic fusion welding, or fusion and extrusion welding, should not be confused with techniques such as gluing, soldering, or brazing, which do not ultimately melt the base material and have a seam or a weakness in the joint between the two materials. Conversely, extrusion welding heats all 3 materials, base A, base B, and the filler material to a prescribed temperature based on material thickness and type to create a homogeneous weld pool where we encourage molecular alignment across that seam. And as we'll see in a second here when we talk about material testing, the weld seam is actually the strongest part of the section. The weld seam will have more material, will be a thicker section, and when we run it through tensile strength testing, our expectation is that the other material, either the A or B materials in the system, will fail and not the weld itself. So with this, we're able to create a huge array and an infinite configuration of different types of systems by use of extrusion welding and polyethylene. Much like you can think of, we can weld almost anything and create almost anything out of steel. The same would apply to polyethylene, where we can create almost anything out of polyethylene using thermoplastic fusion welding. Here's a snapshot of an extrusion welding gun being utilized. Just the concept is essentially we apply a granulate funnel or wire reel feed of polyethylene through a small extrusion chamber in the gun. That heats that. Simultaneously, hot gas or air is fed through the unit to heat the base materials A and B to the prescribed temperature. And then we have a welding shoe, which is actually pre-designed for the project based on the joint configuration and the stress and strain that we're going to apply to that joint. There are standards and quality control procedures to ensure that we have the right geometry for the loads that are going to be applied to that. And we'll talk a little bit about that when we cover finite element analysis modeling. Here's just a photo for those that are not familiar with extrusion welding. As you can see, these guns are quite large, sometimes 40, 50 pounds, and operator fatigue can come into play, and also the quality of quality control and training of the operator is critical to ensure we have a high-quality product delivered to the project site. This is just a snapshot from the fundamentals of thermoplastic fusion welding that kind of speaks to the critical nature of operator training and quality control procedures, the temperature of the nozzle, the base material, preparation of the joint, the amount of pressure applied to the system, and also the rate at which material is being applied are critical operator-dependent elements. So we talk about this because it's important to note that anyone can buy an extrusion welding gun and weld something in their garage. However, it's very important for engineered systems that need to last 100 years to have a rigid quality control certification and training program in place for that operator. Uponor adheres to DVS welding standards. Our operators are DVS certified, and that is the oldest, I guess, most stringent welding standard that's been around for a while. But there's also AWS B2.4 2012, and Uponor falls under B2.4's guidelines as well. So there are those two standards in play throughout North America and the world, and it's important for any company that's manufacturing polyethylene systems to adhere to at least one, if not both of those standards. Additional standards, as you might expect, would be ASTM standards. We're not going to go through this list, but we will cover some of these in a little bit here when we talk about underground installation and also acceptance testing for drawdown in a second. But it's important to note that there are extensive ASTM standards in place that would govern the design, fabrication, and installation of any thermoplastic welded system. And when we work with an engineer or client to develop a system and specification, we will prepare the relevant ASTM specifications and ensure that the project meets that. So after we have extensive quality control testing, certification of our welding technician, and a quality control plan in place, we also have to have quality assurance testing. And the three lines of defense for quality assurance are visual, pressure testing, and internal leak testing, or exfill, infill testing as we refer to it. As one might expect, just like steel welding, first line of defense is visual inspection. This is where we're going to look for a heat-affected zone or a dull-appearing haze that follows the weld. So we're looking for a consistent dull-appearing haze to follow the weld gun. If we see shiny splashes of material or inconsistency in that haze, we have a problem. We either need to test that section or remove that weld, regrind it, and reproduce it. So when you look at a polyethylene weld, you're going to want to look for a dull-appearing haze to follow that weld seam. The other line of defense, which we'll talk about here in a second, is pressure testing of the internal voids. This is actually unique to wheelite in that we have an annular space that is generally continuous throughout the structure, and when we break that annular space with a penetration, a pipe penetration or something else, we can actually test across that penetration by pressurizing the annular space, and we'll show you some photos there. We also frequently are asked, especially on combined sewer projects, to develop in-field leak testing and acceptance programs. This is an important thing for us to identify early in the project that there's going to be a 24-hour drawdown or infill, exfill test to develop the specification for that project to ensure that when we go out into the field to test this this application for leakage, it's done correctly. And we'll work with folks to do that. But it is very common for us to have to conduct 24-hour drawdown, infill, or exfill testing in the field, and that is governed by 2487. Here's a photo of our pressure test. Before any structure leaves the field, or even in the field, if we're doing welding in the field, we can pressurize that annular space, as you see there, to ensure it holds pressure. And it's a great quality control check that is actually exclusive to the wheel-light profile and gives us an advantage in fabrication and delivery of a watertight system. That is something we do very frequently and part of our quality control plan. So now that we've talked about a little bit about thermoplastic fusion welding, I'd like to cover pipe and vessel design. Engineers and clients should be familiar with pipe and vessel design, where it comes from. We don't have a lot of time to cover this at length, but this is just a familiarization. Where wheel-light is concerned, we're concerned with ASTM F894, and that's where we describe the stiffness of the material as a ring stiffness constant. And some might be familiar with solid wall pipe, where we describe the stiffness of the material as a pipe stiffness. They're interchanged inaccurately quite frequently. They are different. So solid wall pipe refers to a pipe stiffness, which is described as a prescribed deflection position at a prescribed speed on a prescribed sample length. And then we have ring stiffness constant, which is really weighted for size. And the ring stiffness constant is deflection divided as a percent based on the sample length in feet. Slight nuances or differences between the two, but we should be familiar that the two are different. And as one might expect, the two pipe stiffness, PS, and ring stiffness constant, RSC, can be related. And the basic equation, as you can see there, is equation X1.2, which basically relates a load times over a travel times a sample length. As you can see, there's the basic equation. But all pipe design is in accordance with PPI, Plastic Pipe Institute Chapter 6, for solid wall and wheel-light. And as you can see there, the deflection and performance of that pipe, buckling, strain, they're all based on Spangler's modified Iowa formula, as you can see there. And I encourage everyone to visit Plastic Pipe Institute if they'd like to understand a little bit more about pipe design for both structural profile wall, F894 pipe, and solid wall pipe. You can visit PPI's website, and they have an excellent resource there, and particularly Chapter 6 of PPI would be that governs this. And this applies to horizontal pipe configurations. In lieu of everyone becoming an expert on plastic pipe design, we've actually developed a very handy design calculator online that will calculate buckling, strain, deflection of any horizontal pipe system. You can simply input some parameters for the project into the buried pipe design calculator, either for solid wall or structural profile wall wheel-light, as you can see there. Here's just a snapshot of the output that tool provides. And you're free to use this, log in and use it at your leisure. Alternatively, you can contact us, and we'll be happy to run that for you for any given project. But pipe and vessel design and rectangular structure design is all based upon some material testing. Uponor is one of the few companies in the world that has run full-scale deflection testing on all its diameters for all its pipe. We have a full-scale deflection testing facility in our Huntsville location where we'll actually test our pipe, and we have NSF testing. So that deflection testing is actually the basis of our design, and it's very important for any manufacturer that produces polyethylene pipes, whether it's structural profile wall or solid wall, to be able to show that their deflection testing of their material meets the ASTM, and their design is in line with that empirical data. We also, as I mentioned earlier, conduct tensile strength testing or destructive testing on our systems, where we'll put the system under load, in this particular case 2,900 psi in a tensile load, and as we would expect, we would see the failure of the material in the profile itself, not in the weld seam, and that's what you see in this particular photo. On the photo on the left, you can see we've taken a coupon sample, put it in the tensile strength machine. You can see the weld on the top and the weld on the bottom, and as we would expect on the photo on the right, it is the profile between the two welds that fails under load, which is what we want. We want to ensure that that weld seam is the strongest part of the section. And then for any given project, as part of our quality control and quality assurance program, we can provide a sample to our clients to demonstrate that the material met standards and provide a report and actually provide the samples if they so desire on any given project to just reinforce that. So that was a little bit about pipe and vessel design. But, that's for horizontal pipes. Any pipe or horizontal vessel, whether it's a CSO storage structure that's run in a horizontal condition, the deflection, buckling of the system can be designed around pipe and vessel design in accordance with PPI. However, when we start to penetrate the structure or build baffle walls, put manholes in it, bulkheads, or do anything that goes beyond pipe and vessel design, we need to conduct a finite element structural analysis. So again, as I said, bulkheads, risers, penetrations, these don't fall under pipe and vessel design, and they need to be looked at carefully in the design of a structure. There's two ways to do this with finite element, and we will employ both from time to time depending on the application. The first is CANDY, finite element analysis, which is a FEA program that does a 2D planar slice through the structure to model the backfill, the structure itself, and also the vehicular loads, if any, applied to the structure to determine the deflection of the system. We'll show you some photos there. We also conduct a three-dimensional, either ANSYS or Inventor, finite element analysis that will actually model the structure in 3D in many nodes, and we can apply loads to that. And so I'll show you some examples of that work. So you can see here is a bulkhead that has a pipe penetration. That would not fall under pipe and vessel design. So in order for us to ensure that's going to meet allowable deflection and the loads that are applied to it, we have to model that in our 3D FEA, and then we can determine the deflection of the material. If that deflection exceeds allowable tolerance in the range of L over 1,000, we can reinforce the annular space in the system, or we can provide additional external reinforcing. As you can see on the bottom right of photo right, we actually ran a profile, and we can put steel inside that if necessary to improve the strength of the system when it's required. As I mentioned earlier, CANDY FEA is a 2D slice. CANDY 2D FEA is a two-dimensional slice. As you can see in these photos, we model the subgrade. We model the non-critical backfill zone in the photo on the top is the yellow area and what we refer to as a non-critical backfill zone. And then we have the CBZ, which is the critical backfill zone. And then we can apply loads to the system and determine the deflection of the structure. So these are some tools that we have to take our systems beyond pipe and vessel design and ensure that the structure is going to meet our design requirements. So one question that comes up frequently is, okay, so wheelite and wheelite modular systems are 1/10 the weight of concrete. How do you guys counteract buoyancy? Is buoyancy a concern? And the answer to that is it's fairly simple. We design all of our systems assuming a submerged condition or the vessel is fully submerged in the field. That's the most conservative approach, but we find that it gives us a sense of calm in the face of uncertain groundwater table information. Typically, we have seasonal high groundwater issues, and it's often hard to pin down the groundwater table. So we find that it's best to approach the design assuming a fully submerged condition. And then we can rely on the soil column around the structure or above it to provide additional buoyancy anchor. For vertical applications, we would extend the base plate to capture more soil column and can do that up to a 14-foot shipping width. And then for horizontal systems, we rely on a strap and anchor system. It's fairly straightforward. For those that aren't familiar with buoyancy, buoyancy is calculated based on the volume of displaced water, which is basically the volume of the vessel times the specific weight of water, or 62.4 pounds per cubic feet. And then we basically have the weight of the structure is the force down, and then we also have the soil columns load on the horizontal projection. For vertical vessels, you can see there on the isometric on the left, we would extend that base plate to capture more soil column up to a 14-foot width. When that 14-foot width is exceeded, we can't ship that efficiently. We would just cast a simple concrete collar around the base, as you can see there on the bottom right, to ensure that we had sufficient horizontal projection under the soil column. We also have a handy design calculator, as you can see there, that we're happy to run for you or share to quickly determine the necessary buoyancy countermeasure for any application. For horizontal, as I said earlier, we would rely on a strap and anchor system, same principle as vertical, where we're trying to increase the horizontal projection under the soil column and then transfer the vertical force upwards from buoyancy from the system through a strap to the anchors as you see there. We also have a prefabricated system for buoyancy that can be shipped to the project site, where we'll actually use a wheel-like pipe, fill it with concrete and rebar, and ship it out to the project along with the system. Then the contractor can easily set that adjacent to the structure to counteract buoyancy. And all of these particular buoyancy countermeasures would be designed custom for any project, and we're happy to help you through with that. So before we get into a couple project profiles quickly, I just want to discuss backfill standards. Buried pipe structure design, these are flexible conduit structures that are basically soil structure interaction systems that rely on high-quality backfill compacted to 90% modified Proctor in uniform lifts on both sides. Most folks know that, but it's important to talk about the standards related to that. And the primary standard that we would adhere to would be ASTM D2321. This particular standard defines material gradation, placement, and compaction of material around any polyethylene structure. It also defines acceptable subgrade parameters. When we have all those parameters, we can accommodate the project by simply adhering to ASTM D2321. If the project doesn't have those, or we're not capable of achieving that, we can actually run the actual project profile parameters in our Candy analysis and determine whether the actual subgrade condition or backfill available for the project would meet our design criteria. But our first line of defense is to simply adhere to ASTM D2321. If we're not able to achieve that, then we would have to run a Candy analysis to confirm performance of the system. So ASTM 2321 defines, again, as I was talking about earlier in the Candy analysis, defines a critical backfill zone A, non-critical select backfill zone B, subgrade, and then the surface above the structure. That same consideration in a rectangular form would be the same. And what it does is in that zone A, it defines a critical backfill material, which is really a class A1 or A3, if you're familiar with the ASHTO soil groups, or a class 1, class 2 material. So that's a high quality, well-graded material placed and compacted in uniform lifts and to a modified 90% Proctor. In the zone B outside, we're a little bit more forgiving, and again, that's on the outside of that critical backfill zone. We were allowing other materials. We're even allowing a little bit of clays or CLML materials. As long as they're compacted to 90% Proctor, we're in good shape. So ASTM, I won't read this eye chart, but it does define those materials a little bit more, and this is the basis of our backfill specifications that we develop for any project. So some key points on backfill before we cover project profiles briefly are that essentially, the soil bearing, native bedding of the surrounding subgrade needs to be about 2,000 net allowable, 2,000 PSF net allowable. If we can't achieve that, then we need to know that and either provide recommendations for geotextile gravel improvement to the subgrade, or we can account for that lower net allowable bearing of the existing soils in our Candy analysis and determine whether or not it's acceptable. Frequently, design engineers don't really have good information for the net allowable bearing or the existing subgrade bearing for any given project. So the specification would call out to have that, but also identify that the geotechnical engineer of record, quality control inspector, should confirm that a 2,000 net allowable is achieved once they open up the excavation. The next 2 points are important in that we want to make sure that the backfill proposed and delivered to the project meets the requirements of 2321. Occasionally we run into projects where alternate materials are substituted for backfill, either inadvertently or on purpose, and that's not a good thing because the system is designed assuming certain backfill requirements. So if we're going to deviate, we need to know about that and account for that in the design. Secondly, it's important to know that we need to place and compact the backfill in accordance with 2321, which is very simply uniform lifts on both sides compacted to 90%. And so as you can see there on the bottom photos there, we have a system on the left that's been installed correctly, excellent subgrade preparation. And we have another system in the middle where you can see them bringing the backfill up in uniform lifts on both sides. And then we have the photo on the right, which they don't have the acceptable amount of space outside the structure to compact that material, and they're also not bringing it up in uniform lifts. They're simply dumping that material around the structure, which is a no-no. So, we want to develop quality control standards to set it up such that the project is installed correctly, it uses the correct material, and it's brought in even lifts to ensure that it lasts the design life of the system. So a couple minutes left here. We'll cover some project profiles. This is the more interesting part of this presentation. The first project I'd like to talk about, we're very excited about, we just closed this one out, is the St. Agathe Combined Sewer Overflow Project. This project utilized multiple diameters to achieve 260,000 gallons of storage in a manifold type configuration. We used, I would say, medium diameter manifold header system, a 36-inch manifold system at the header of the structure. And then we were able to accommodate the existing site layout and also the geotechnical considerations for rock bearing and excavation limitations to get the layout and get the volume of storage required to provide CSO overflow mitigation for this particular project in Quebec. Just shows you our ability to modify and configure our system to meet any project's requirements. Here's a snapshot of that project going in. As you can see there on the bottom right-hand photo, there's the header openings that would be connected to what is shown right above it, the 36-inch header system that's actually manufactured out of solid wall sclare pipe. And that's actually systems on its side. What you see there is the riser or access riser, and then the header systems are the smaller stubs coming off of that. We would also have access ladders inside the structure to encourage access. And then that riser could also be extended vertically by welding another section on top of it to extend it to grade. That's just an example of a large diameter detention structure for a CSO application. Another project we recently closed was the LA County Federal Courthouse. This one was very interesting. This was a rainwater harvest and reuse application for 106,000 gallons. The big challenge on this project, it was immediately adjacent to a roadway and the building, and we had to design the structure to remain outside of the zone of influence of the structural footings, which we were able to do. As you can see in that configuration, this is a photo of the installation. Here you can see an actual isometric of the structure. This was actually 4 11-foot diameter sections that were delivered to the project, and then field extrusion welded to create a 100% watertight system. On this project, it's also interesting to note that we provided a submersible pump station or a standalone vertical submersible pump station to remove the submergence depth requirement for the pumps from the vessel itself. And this is a more efficient design because the particular pumps for this project had about a 1.5-foot submergence depth, which is basically inactive hydraulic storage that can't be utilized. So we want to bring that outside the system to get the most storage inside the vessel as possible and minimize the footprint of the project. Here's a couple of snapshots of some internal components. We showed you some of these photos earlier, these isometrics. The isometric on the left-hand side is the submersible wet well itself, and the other photos are internal controls for energy dissipation, drawdown, and TSS removal to encourage high quality of water. This is a CSO storage structure, 60-inch wheelite system, where we actually connected these structures to concrete systems. It's important to note that we could also do these header manhole structures in polyethylene as well. Larger diameter structure here, the Hall Crescent CSO project. We used a 120-inch wheelite that was field welded, and we had about 250 linear feet per barrel. So it's continuous 250 linear foot run of a 120-inch wheelite with field welded joints that had to pass a 24-hour drawdown test for infiltration and exfiltration. Example of a manhole project we produced 16 manholes for the Denver airport. These were replacement manholes replacing concrete structures that had deteriorated due to H2S and glycol. And these particular manholes were fabricated to accommodate aircraft loading as well. As you can see, we have a top riser that extends. On top of these structures would be a cast-in-place rebar reinforced load relief slab to mitigate the high wheel loads of the aircraft and distribute those loads to the soil. And that's something we can do on any project to accommodate the vehicular or aircraft loading with a load relief slab above the structure, standard design practice. Another stormwater project here. This is 350,000-gallon storage structures of 120-inch wheelite, just to kind of demonstrate our capabilities and the size and magnitude of storage structures that we can provide. We talked a little bit about this earlier. This is a UV, potable water UV contact system. It's an above-ground structure. Horizontal pipes need to have haunch support when they're full of water, so we combine the wheelite panel and wheelite vessel to create an above-ground system to accommodate UV contact in a potable water facility. So it's just an example of the versatility of the material and our ability to provide a solution for any given project. We talked a little bit about this one earlier. This is just an example of how we can provide large diameter manholes, junctions, and we can just move forward from there. And the last project before we terminate here and go to question and answer is basically a stormwater overflow project where we had an inline stormwater detention structure. We removed the existing small diameter pipe and replaced it with a large diameter structure and outlet control to provide stormwater relief in line with the existing storm drain. Also important to note that we provided both RCP and PVC dissimilar material connections into the structure. And so that is the last project profile I have. And with that, if there are any questions, we can jump right into them.
Thank you very, very, very much, Brian. That was fantastic. And thank you, Grant, as well. As Brian said, this is the question and answer portion. We are coming to the top of the hour, though, and we understand people's time constraints. So we're going to keep this section pretty brief, but I do want to remind folks that if you do have a question you want to ask and you haven't had an opportunity to do so, you can still do that. There's a Q&A widget at the bottom of your console. If we don't get to your question now, the presenters will receive those and they'll be able to answer you offline. But before we let you go, let's try to tackle just a couple of questions here. We have one viewer that's asking, can this be applicable to a leachate storage tank as an alternative to glass-fused steel tank? And they suggest dimensions of approximately 10 meters high, 20 meters in diameter. What do you think about that?
I'll take.
Oh. You're going to take that? Okay.
Sure. Well, HDPE is very inert material. Just a comparison to that, when we do wastewater treatment facilities where they may be hitting maybe a membrane environment where they're hitting it with about a 2 pH to a 12 pH, hit it with chlorine, hit it with surfactants, so very numerous chemicals. We've never had an issue with that. When it comes to leachate, again, because it's a landfill, different materials, yes, the HDPE material will be very inert, and we have used HDPE tanks as well as the wheelite piping for conveyance within leachate. So we have a lot of practical experience and case histories which we can draw from. So the answer is yes, you can.
Terrific. Great. Thank you very much. And then one more quick question before we wrap up today. How is the long-term deflection of HDPE wheelite structures handled in design?
Want me to do that one,
Brian? No, you got that one.
All right. So, yeah, long-term deflection or long-term applied load is actually part of the PPI design. So when we put in the loading on the structure into PPI design, we actually enter in the design life or the duration of that applied load. So we actually design the structure to withstand a 100-year applied continuous load duration of that material, and then we use PPI, and this is for horizontal vessels. And then when we run a Candy analysis, we account for the amount of load applied to the structure and then use the same material properties that Grant mentioned earlier in evaluation of that load and the total deflection, strain, moment, and shear on the structure, and account for that in our design process as well. And that's all part of the design calculations package that we typically prepare as part of our submittal process, whether it's horizontal pipe, baffle walls, bulkheads, or wheelite modular. That is accounted for and in accordance with PPI.
All right, terrific. Brian, thank you very much. With that, I'm going to have to wrap up now, and so on behalf of Waterworld and Penwell Corporation, I just want to thank today's speakers, Grant Thornley and Brian McGuire, as well as our sponsor, Uponor Infra, for today's presentation, Put a Dent in Your CSO Event Using Structural HDPE. Just one more quick reminder, today's presentation will be archived within 24 hours, and it can be accessed from the homepage at waterworld.com. And a reminder email message will also be sent out to all registrants with a direct link to that archive. We want to thank you all for joining us today. We look forward to serving you with future webcasts. And with that, this concludes today's presentation. Thank you all for participating.